Hello, today I want to talk about the propagation of cosmic rays, which determines the differential energy intensity, which we have seen in the last videos, which follows a path law, and we have seen in the first video that the value of the spectral index gamma depends on the energy range we are observing. The first two transition points at which gamma changes they are called the knee and the second knee, and they represent the points at which galactic heavy elements start dominating the spectrum over galactic protons. And the last transition point is called the ankle, and it represents the point at which extragalactic cosmic rays start dominating over galactic cosmic rays. And for galactic cosmic rays, we will see that the spectral index can be seen as the sum of an injection spectral index gamma 0, which represents how cosmic rays are accelerated by the sources, and a diffusion spectral index delta, which represents the energy-dependent diffusion and escape of cosmic rays from the galaxy. Let's begin with the diffusion of cosmic rays in the interstellar medium, which will determine the diffusion spectral index delta. Before escaping from the galaxy, cosmic rays travel some depth xi, they escape, and the depth we have seen in the last video is the density of the medium in which they travel, in this case interstellar matter, times the distance, which will be the escape distance. Now this depth is also called grammage. So the grammage is rho ISM times x escape, and the distance of escape is c, because they move at the speed of light cosmic rays, times the tau s, the time of escape. And during this travel, something happened. For instance, spallation happened. Let's now consider spallation. Spallation, we have also seen in the last videos, is a process in which a massive nucleus, a heavy nucleus, hits a proton of the interstellar matter, and this collision gives rise to a light nucleus plus some stuff. So we are interested in finding the grammage of escape such that it gives us the ratio light to medium elements found in cosmic rays. This ratio, let's go the ratio, the number of light elements divided by the number of medium elements, and we are interested in the case in which light elements are lithium, beryllium, and boron, and heavy elements are the most common heavy elements, which are carbon, nitrogen, and oxygen. So we're interested in these cases because we have very good data on these ratios, and because we have a very good initial condition on the light elements, because light elements only come from spallation, because these elements are used inside stars to continue the process of nuclear formation, so they are just used as catalysts and they are not emitted by the sources. So in fact, this ratio measured in the solar system is only 10 to the minus 5. Instead, in the ratio measured in cosmic rays, because of spallation, is much larger. RCR is 0.25. So we are interested to see to look for the escape grammage such that our escape, which is our cosmic rays, equals 0.5, and with the initial condition at 0 equals our solar system. which is very small compared to 0.5, so we can set it equal to 0. So we have the initial condition, the final condition. Now we must find the probability of the process. The probability depends on the fragmentation cross-section. The probability is the fragmentation cross-section of heavy nuclei into light nuclei when hitting a proton divided by the total cross-section of heavy nuclei hitting a proton. So this can be written as the fragmentation cross-section of carbon into lithium plus fragmentation cross-section of carbon into beryllium plus carbon into boron plus then we have nitrogen into lithium plus nitrogen into beryllium and so on. Then we have plus oxygen into lithium and so on. And these must be multiplied by the respective abundances. So this must be multiplied by the abundancy of carbon to heavy nuclei, where heavy nuclei are carbon, nitrogen, and oxygen. This must be multiplied by the relative abundancy of nitrogen to heavy nuclei, and this times the relative abundancy of oxygen to heavy nuclei. And of course, these abundances are the abundances found in cosmic rays, because these are cosmic rays interacting with proton of the interstellar medium. And at the denominator, we must put the total probability cross-section of carbon times the relative abundancy plus that of nitrogen times the relative abundancy plus that of oxygen. Now, these values of the probability cross-sections can be found in tables. They depend on the energy, but most cosmic rays have energies on the order of 1 gigaelectron volt. So if we are not interested in finding the grammage per energy, but only a general grammage, an average grammage for cosmic rays, we plug in 1 gigaelectron, the cross sections for 1 gigaelectron volt, which we find in tables, and then we plug also in these abundances, which are found by observations of cosmic rays. In the end, we will obtain a probability of about 0.28. In the last video, we had calculated the formula with the interaction length, which is the mass density of the target medium, in this case interstellar matter, divided by the number density of the interstellar medium times the interaction cross-section. This is equal to the mass of one particle of interstellar medium. Interstellar medium is mostly composed by protons, so this is the mass of a proton divided by the interaction cross-section with one particle of the interstellar medium. The interaction cross-section of heavy elements with protons is about 280 millibarns, where 1 barn is 10 to the minus 28 square meters. The interaction cross-section for light nuclei is about 200 millibarns, and so we can calculate the interaction length for heavy nuclei. It is 6.0 grams per square centimeter, and for light nuclei it is 8.4 grams per square centimeter. Now we must set up and solve the differential equation for the number of nuclei of light nuclei and heavy nuclei. Remember that in the last video we had obtained the formula for the differential equation of the change in the number of nuclei when they interact with a medium, and this was the differential equation was of this form: -1 divided by the interaction length times the number. And so, for instance, for heavy nuclei, we have the interaction length of heavy nuclei, and the solution is Nm equals N0m e to the minus divided by interaction length, and 0m is the initial number of heavy nuclei. And then we have for light nuclei, we also have this 1 divided by lambda L times NL, but this time light nuclei are also produced by heavy nuclei when they interact with protons with a probability p. So we also have minus because when heavy nuclei decrease, light nuclei increase. So minus this times the probability p, and we substitute with this, so we get plus p divided by lambda m times this, which we can write like this: e to the minus divided by lambda m. And so the solution is we can write it as the sum of a homogeneous solution, which will depend on the decaying exponential of the light nuclei, and plus a particular solution due to this term, which will be proportional to this exponential. Now if we plug in the particular solution, then we get b minus divided by lambda m times the exponential equals minus 1 divided by lambda L times this plus p divided by lambda m times n0 m e to the minus xi by lambda m. We can remove the exponentials, so we get for b b times 1 over lambda L minus 1 over lambda m equals p divided by lambda m times nm 0. So we can write b equals this divided by 1 divided by lambda L. We can write this as lambda m minus lambda L times lambda m times lambda L. Lambda m simplifies with this. Let me write better: lambda L. And since lambda m is shorter than lambda L, this is negative. So just to make it more intuitive, we change sign. Lambda L minus lambda m. And we also have the initial condition, and L at the beginning is 0. So we have that a plus b, because when you plug in 0, the exponentials became 1. A plus b equals 0. So a equals minus b. So this is equal this without the minus sign. So we can write NL equals p nm0 lambda L divided by lambda L minus lambda M times e to the minus I divided by lambda L minus e to the minus I divided by lambda M. And this is the expression for the number of light nuclei. Now we want to find the value xi-esc such that this ratio, this divided by this, is equal to 0.25. And we have all the data. Notice that the ratio does not depend on the initial number of heavy elements because it gets cancelled out when you take the ratio. And this means that if you, for instance, if you do a graph of the heavy elements and the light elements, the heavy elements, you can choose an arbitrary value for n0m, and the point at which the light elements will be 0.25 times the heavy elements will be the same for every choice of the initial value. For instance, you could take let's say 1 as the initial value of n0m. So here you have n and here you have xi. Then the heavy elements follow a decaying exponential. The light elements instead follow this, so the beginning they grow, then they go down again, and the point at which xi-esc at which the number of light elements is 0.25 times the number of heavy elements would be the same for every initial value of n0m. So here, for instance, it looks like it is about here. So to find this value, you divide this by this. So this cancels out. You set everything equal to 0.5, and you solve for xi-escape. The result is xi-escape equals 5 grams per square centimeter. So while this looks a small value, remember that there is very little density in the galaxy. So actually the travel distance is very large. In fact, the density of the interstellar medium is 1 proton mass per cubic centimeter. So you can find the escape length traveled, and the traveled length is 3 times 10 to the 24 centimeters, which is 1 megaparsec. This corresponds to roughly 3 million years, 3 million light years. So since cosmic rays go at the speed of light, this means that the escape time is 3 million years. So they stay 3 million years inside the galaxy. Considering that the galaxy is 100,000 light years in diameter, and it is thick 1,000 light years. This can only be explained by cosmic rays being deflected by magnetic fields. And in fact, 1,000 light years, the escape length is 30 times larger than the galactic diameter. Also remember the interaction length for heavy nuclei is 6 grams per square centimeters, and for light nuclei is 8.4 grams per square centimeter. So the escape length is even shorter than the interaction length. So many nuclei also can escape a galaxy without even interacting with interstellar medium. Now that we know how to calculate the escape time, we can calculate for the other energies, knowing the cross-section and the ratio of the light to heavy elements. And we have in particular that the escape time is proportional to e to the minus delta, which delta equals 0.66. So now we can find gamma. And to do this, we set up the diffusion equation in the leaky box model. The leaky box model tells that how cosmic rays diffuse in the galaxy does not depend on where they are, and this is a simplified model, and that the diffusion will depend on a source which injects cosmic rays and how they escape out of this box. They escape with the calculated escape time, and there is also a term of for the energy losses. Then there is a term for spallation. So nuclei receive other nuclei by spallation of nuclei J with a probability Pj I, so that the probability that J turns into element I. But if we solve this equation for primary cosmic rays, which means cosmic rays which are not product of spallation, we can ignore this term. And this term of energy loss is important only for electrons and for positrons, so we can neglect also this term, and we are only left with this, and this. And if you want to solve for a steady state, we put this equal to 0. So we have that the number of primary cosmic rays is equals to the source term divided by 1 divided by the escape time plus the spallation term. The spallation term tau is, of course, lambda divided by c, but we want lambda in grammage, so this is lambda I divided by the density of the interstellar medium, and this is for primaries. So we can write this as qi of e times tau escape times tau p divided by tau p plus tau escape, and we can divide everything by tau p, so we get np of e equals qi of e times tau escape divided by 1 plus tau esc divided by tau p, where tau p we can write it as lambda p, and here c times rho ISM. Because of solar modulation, the Pauli holds for high energies above 10 gigaelectron volts, and so by neglecting this term for high energies, tau escape divided by times c times rho interstellar medium divided by lambda p, so lambda escape divided by lambda interaction is small, and so for high energies we can do this approximation. The number of primary cosmic rays is equals to the source term q times tau escape. Now since tau escape goes like e to the minus delta, and we know that the observed spectra is gamma 0 is 2.7, then gamma equals gamma 0 minus delta with minus gamma 0 minus delta with, sorry, it is right, minus 2.7 with delta equals 0 0.66, or 66, sorry, I meant 6. Then gamma 0 must be 2.1. So the sources which accelerate cosmic rays must accelerate in such a way that the energy spectra has an exponential minus 2.1. So we must now find mechanisms which can explain this power law and which can give a value of 2.1. And the first one who found out mechanisms which can accelerate with this power law was Enrico Fermi in 1949 with his acceleration mechanisms. Now he imagined cosmic rays to be accelerated when colliding with gas clouds. Today we know that the gas clouds are not very efficient in accelerated cosmic rays. They are mostly accelerated by shock waves in supernova remnants. But the mathematics works the same. The only thing which changes is the distribution of the angle of impact that we will see in the end. Imagine a gas cloud is moving in the x direction at velocity u, and particles collide with a gas cloud, cosmic rays. Cosmic rays can collide this way or this way. So head-on collision or catch-up collisions. Catch-up collisions will transfer energy to the gas cloud, and head-on collisions will make cosmic rays gain energy from the gas cloud. In the frame of reference of the laboratory, let's say that cosmic rays, a cosmic ray has a momentum for vector of energy E divided by C and px. We consider now the component along x, so the component along the velocity of the gas cloud. Then in the rest frame of the gas cloud, which is moving with velocity u with respect to the laboratory, it will be E prime px prime. We consider relativistic collisions. So in the rest frame of the gas cloud, after the collision, the cosmic ray will have the same energy as before and opposite momentum along the direction of the along the perpendicular direction. So now we can calculate the energy after collisions. Before collision in the rest frame, in the laboratory frame, before collision, we can apply Lorentz transformations, and we have that the energy is E prime divided gamma times E prime divided by C minus U divided by C plus U divided by C, because the gas cloud is the frame S prime moving in the direction of X, so plus U divided by C times Px prime. After the collision, this becomes E star divided by C, and it will be E prime remains E prime, and P prime becomes minus P prime, so P prime X. So we have minus U divided by C Px prime. Now we can write these in terms of the laboratory energy and momentum with another Lorentz transformation. So we get equals gamma squared times E divided by C minus U divided by C Px minus U times C times Px minus U divided by C E divided by C. This is gamma squared times E divided by C minus 2 U divided by C times Px plus u squared divided by c squared times E divided by C. Now we can multiply by C, so we found E star, and we can also approximate gamma squared with a Taylor expansion, because gamma squared is 1 minus u squared divided by c squared, and this is about 1 plus u squared divided by c squared. So we can write 1 plus u squared divided by c squared, and now we must multiply this by c, times E minus 2u px plus u squared divided by c squared E. Now px can be written as m gamma Vx, and Vx is V times cosine of theta. Theta is the angle with respect to the perpendicular to the cloud, so with respect to the x-axis, and this is, since E equals gamma m c squared, this is E times V divided by c squared times cosine of theta. And so we can substitute here. We can write E star equals 1 plus u squared divided by c squared. Then we take out E here, and we get 1 minus 2u times V divided by c squared times cosine of theta plus u squared divided by c squared, with E taken out. So we can now multiply this by this and ignore the higher order terms. So we get E star equals zero order, we have 1. Then first order, we have minus 2 V divided by C times U divided by C cosine of theta. And second order, we have this and this, plus this and this, so plus 2 u squared divided by c squared. So in the end, we will get our energy difference delta E equals E star minus E equals to minus 2V divided by C u divided by C cosine of theta plus 2 V squared divided by C squared times E. And sometimes you see this written with a plus sign here, because we have chosen the convention in which the gas cloud moves in the direction of the x-axis, in the positive direction of x. Instead, if we had chosen that the gas cloud moved opposite in the Lorentz transformation, we would have had an opposite sign, which we can get to those simply by reversing the sign of u. So if we substitute u with minus u, here we get a plus sign. And so in our convention, the gas is moving this way, so the head-on collisions are those in which the angle theta has a negative cosine. These are the head-on collisions. So in our convention, the head-on collision are for cosine of theta negative. In the other convention with a plus sign, where the cloud is moving in this direction, then the head-on collision are those with a positive cosine of theta. So in this other convention, the head-on collision are for cosine theta positive. So you see here that for head-on collisions, cosine of theta negative, then this is positive, and the particle in the laboratory frame always gains energy for head-on collisions. Instead, for the other types of collision where cosine of theta is positive, there are many values of theta for which the particle loses energy. Fermi considered collisions with a gas cloud. He thought that it was gas cloud which accelerated cosmic rays. So in this case, collisions are both head-on and catch-up. So the collisions happen in every direction, and they all cancel out. So on average, this cosine is 0, and so the difference in energy is 2 u squared divided by c squared. This is a very inefficient way to accelerate cosmic rays because u is very small, the velocity of the gas cloud with respect to the velocity of cosmic rays, and he would acknowledge this inefficiency in a paper in 1954, the year of his death, but he will not be able to find the solution. If there is an environment which allows only head-on collisions, for instance, this would be very efficient because this term will not be 0, it would be positive, and so it would, since it is first order, it would dominate over this other term, and it has v over c, and v is quite large. In fact, we can find the average of cosine of theta for head-on collisions only, so only for cosine of theta less than 0. And in this case, to find the average, we must find the number of particles with a certain value for cosine of theta. We must sum them times the cosine of theta. We must take the summation, so the integral divided by the number of all particles. So the integral of dn cosine of theta without multiplying by cosine of theta. And this number, dn, it is given by the flux times, the intensity times area dA time dt and angle d omega. This number dn is positive because the flux is negative and the area is an area with sign. In fact, cosine of theta depends on this number dn depends on cosine of theta not only through the differential angle, which is sine theta d theta d phi, the differential solid angle, but also through the area, which is a common area for every direction d prime, which would be the area of incidence of the intensity times cosine of theta. So if cosine of theta is negative, the flux also is negative because it is a head-on collision, and so the total number is positive. If you remember, we did something similar in the first video when finding the flux from the intensity. We considered that when hitting a surface area dA prime, the intensity of cosmic rays from this direction has a contribution through this area dA, which is equals to dA prime cosine of theta. Although in the last video, if I remember correctly, we called this area dA and this area dA prime. Anyway, so is every piece, for every differential angle, we have a contribution in dA, which is dA prime cosine of theta. So we can now do this ratio. We get, we can assume isotropy, so we take out this, we have the flux, we take out also dA prime, we take out dt, and we take out d phi, although integrating in it would be 2 pi here and 2 pi here. We do not even need to integrate 2 pi, we just take it out, and then it cancels out because these terms are in the differential, which is present in both integrals, so they simply cancel out, and we are left with the integral of cosine of theta times the remaining terms here, which are cosine of theta again, sine of theta, d theta, and at the denominator we have this, but without the cosine of theta, the integral of cosine of theta, sine of theta, d theta. Now we can find, write sine of theta d theta as minus cosine of theta. Sorry, minus d cosine of theta, because d cosine in d sine is minus sine. And so by doing this, we call cosine of theta, we call it x. So we have the integral of x squared dx, the minus cancel out, and the integral of x in dx. Now we are doing the integral for head-on collisions. For head-on collisions, the cosine of theta goes from 0, sorry, not from 0, goes from theta goes from pi half to pi. Then the rest was achieved by integrating by d phi. So we have only this piece of circle, and so we are integrating from 2 pi to pi. So from 0, from cosine equals 0 to cosine equals minus 1. So from x equals 0 to x equals minus 1 of this integral, divided by from 0 to minus 1 of this integral above is x cubed divided by 3 from 0 to minus 1, and this one below is x squared divided by 2 from 0 to minus 1. So this is minus 1/3. Let's write here. The average cosine is minus 1/3 divided by 1/2, which is minus 2/3. So this is the average cosine, which we can plug in here, minus 2/3. So we have two possibilities, both head-on and catch-up collisions, in which case we get the second order Fermi acceleration, because in this case the average cosine is 0, so we only have the second order term which dominates the energy difference. And the other possibility is only head-on collisions, in which case the average cosine is minus 2/3, which plugged in here gives the first order Fermi acceleration, because this time this term is positive and it is not 0, so it dominates over the second order term. And so in this case the energy is given by this term with minus 2/3 as the value of the cosine. So plugging in, it becomes 4/3 V divided by C, U divided by C times E. And we could write this more compact. So this is the value for the first order Fermi acceleration. Enrico Fermi had no reason to believe that only head-on collisions would happen, and he remains stuck to this form of acceleration, the second order Fermi acceleration. In the 70s, astroparticle physicists would apply this Fermi acceleration to only to environment with only head-on accelerations, because they realized that when a supernova explodes, it releases shockwaves, and these shockwaves create turbulences in the magnetic fields, and these turbulences in the magnetic fields are able to deflect back cosmic rays. So when a cosmic rays hits supernova remnants, so an explosion, when a supernova explodes, there is some gas which expands, which is the supernova remnants, and cosmic rays collide with these, like in a head-on Fermi acceleration mechanism. And when they bounce from the collision, the turbulences in the magnetic field surrounding move the particle back again to the shock wave, and so in the end the cosmic ray can collide many times with a shock wave. It can do this until it has enough energy to escape the turbulences of the magnetic field, because at that point it will have a too large Lama radius to be deflected by the turbulences, and it will escape from the supernova and travel to the universe with that energy. Plus, considering that cosmic rays reach the speed of light pretty quickly, we can further simplify this by setting V equals C. And so we only have U divided by C times E. So Fermi acceleration mechanism gives this expression for the energy after one collision, starting with energy E0, and this constant of proportionality B is, in the case of a shockwave environment, the first order expression, and in the case considered by Fermi of a gas cloud, we must plug in the second order expression. In any case, this expression for the energy gained gives a power law for the energy spectrum. To see this, let's consider that after a collision, there is a probability P of doing another collision, and a probability 1 minus P of escaping the acceleration region. Well, in this case, after K collision, we will have energy Ek equals B to the power of K is 0. Let's call this energy E. And the probability of reaching the stage is P to the power of K. So the number of particles which reach this stage, so the particles which do at least K collisions, so the particles with energy greater than E, will be P to the power of K times N0, where E0 is the initial energy of the particle, and N0 is the initial number of particles. And so we can now put K out of the exponent by taking the logarithm. So we can take the logarithm of P divided by 0, which is K logarithm of P, and logarithm of n greater than E divided by N0, which is K times the logarithm of P. Now we want to find n in function of E. So we write we isolate k here, we plug it in here, and we take the exponential. So first we have the logarithm of n greater than e divided by n0 equals logarithm of b divided by logarithm of b times the logarithm of e divided by e0. And so n greater than e divided by n0 by taking the exponential. This we can call it alpha. We can plug it here inside the logarithm as an exponential. So when we take the exponential, we will have, sorry, as an exponent. So when we take the exponential, we have n divided by n0 equals e divided by, so equals, yes, e divided by 0 to the power of alpha. And now we have that n greater than e is, this is the number of particles with energy greater than E. If we want the number of particles with energy equal to E, so the differential number of particles dn of E with energy from E to E plus dE, then this is the differential of this. So dn equals n0 times the differential of this power. So if we want to find the derivative with respect to energy, we take the derivative of this with respect to energy, and we get n0 alpha divided by E0 times E divided by 0 to the power of alpha minus 1. And we have that, obtain this proportionality with alpha minus 1 equals to gamma 0. We know that gamma 0 is about 2.1. So we have that alpha must be about minus 1.1. So let's look at what the probability must be for alpha to be about 1. So for alpha to be about 1, we write here, we consider the shockwave environment. So we write 1 plus divided by 3 divided by c. And we can do a Taylor expansion because the logarithm of 1 plus x is about x. So alpha, to make Taylor expansion of a certain numerator, we would like to write this as 1 plus something. So we can, for instance, since p is a probability of doing another collision, we have that p is equal to 1 minus p escape, where p escape is a probability of escaping the acceleration environment. And so we can write this as 1 minus p escape. So we do the Taylor expansion of these terms. We have minus p escape divided by 4/3 u divided by c. And so this is minus 3c divided by 4u times p escape. So in order to have alpha about minus 1, we must be a probability of escape of about 4u divided by 3c. And we have models for shock waves from supernovae which replicate a similar probability. And this is one of the reasons for which today we think that supernova remnants are one of the main environments in which cosmic rays are accelerated. To calculate the order of magnitude of the maximum amount of energy at which cosmic rays can be accelerated by supernovae, we write Fermi acceleration in this form. So this is the difference, is the gain of energy after one collision, and so this eta is simply b minus 1. This is eta for the first order mechanism. This is for the second order mechanism. For a supernova, we consider the first order mechanism, and we have that a typical supernova might expand at a velocity of 2% the speed of light, and it may last for 1,000 years. So it will reach, during this expansion, the acceleration region will reach a radius of u times the time of expansion, so about 20 light years. The turbulence is caused by the shockwave in the galactic magnetic field, have a cycle, a lambda c, and they bring the particle back at a velocity, at a speed u, at a time t cycle equals to lambda c divided by u. And these the turbulences which are efficient in bringing the particle back to the shockwave for another collision are the turbulences with a cycle length which matches the lemma radius of the particle. So we can write this as lemma radius divided by u. The lemma radius is p divided by z e b, and p for a relativistic particle like the cosmic ray is e divided by c. So the ratio delta E divided by Tc, so the energy gain after one cycle divided by the amount of time for this, so the energy gain after a collision divided by the amount of time necessary to do that collision is equal to eta E0 divided by Tc, which is E times at E B U C. And this energy is zero, which is the energy of the cosmic ray before the collision. And we see that this quantity does not depend on energy. We can write eta as 4/3 U divided by C. And this quantity does not depend on energy. So this is the rate at which the rate of energy for every delta E and every delta T. So for instance, if you want to find the maximum amount of energy, we must take delta E, the energy energy gained by the cosmic rays for the total time of existence of the supernova. So we write here E max, and here TSN, the time of existence of the acceleration region. So the maximum energy is this times T supernova. And we can multiply U by TSN, which gives RSN, the radius, the maximum radius of expansion of the supernova. And so we can plug in here the radius. Here we plug in the galactic magnetic field, and here we plug in u, which is 2% the speed of light. And so we will obtain in the end something of the order of 10 to the 14 electron volts, which is pretty close to the knee. The knee is at 10 to the 15 electron volts. And furthermore, this energy, this expression is this energy is proportional to that. So the energy for one proton is, according to the expression, the maximum energy is 10 to the 14 electron volts, while the energy for a nuclear of charge Z is Z times the energy of the proton. And this is exactly what happens at the knee. At the first knee, the proton is interpreted as the proton which cannot be accelerated more than that. So the first knee is the maximum energy for the proton, which is around here 10 to the 15, or according to this 10 to the 14. Then the knee, the exponent, the spectral index, goes from 3.1 to 3.3, because in the meantime also the other nuclei stop being accelerated because they reach their limit energy. For iron has 26, that equals 26, so the knee for iron will be at 26 times the knee of the proton. And in fact we have that the knee of heavy elements is at around 10 to the 17. This is the last knee, this is the second knee, and which is 100 times the knee of the proton. And so we have obtained the structure of the knee with this. So as a summary, for the acceleration of cosmic rays in the galaxy, we have seen Fermi acceleration mechanism, and evidence for this mechanism, whatever the order of the mechanism, is that it provides a power law, and the power law is what is observed. And for supernova remnants as a main source of cosmic ray acceleration, the evidence we have seen this in the first video, the energy balance, so that the power of cosmic ray energy emitted by the galaxy, so cosmic rays escaping the galaxy, is equal to the power emitted by the sources inside the galaxy. So P emitted is the power here emitted by the sources, and P escape is the power escaping the galaxy, so emitted by the galaxy in the rest of the cosmos. And this energy balance works perfectly if the emission sources are supernova remnants, which are about 3% in the Milky Way, and they also replicate the correct value for the spectral index of injection, which is about 2. We have seen before, and we have also seen that it replicates the knee structure, because the maximum acceleration obtainable by supernova remnants we have seen is proportional to the charge, and it is around the knee range of energy. Then we have also for energy past the knee we need other sources, and some candidate galactic sources for acceleration past the knee are neutron stars and pulsars and stellar massive black holes. However, when energies reach the ankle, these cosmic rays are no longer confined with the galaxy by the galactic magnetic field, because they have a too large Lama radius, and so they escape from the galaxy. So we think that most sources of cosmic rays for energies past the knee, so for energy past the ankle, most sources are of extragalactic origin. So as a summary of the knee, meaning of knee and the ankle, the knee is when supernova remnants fail to accelerate. So when the main source of acceleration in the galaxy fails to accelerate cosmic rays, at that point we have less cosmic rays because we have only these sources of acceleration, and the angle is when galactic confinement fails. At that point, most cosmic rays escape from the galaxy, and so most cosmic rays we observe in this region of energy are of extragalactic origin. So let's now explore the cosmic ray propagation outside the galaxy. When considering a distant source like a galaxy, we must take into account that light emitted from it will be observed at a different wavelength than the wavelength of emission, because it will experience a Doppler shift depending on the velocity at which it is moving. And if the galaxy is approaching us, light will be blue shifted. If it is moving away, it will be red shifted. This is because of the Doppler effect. So imagine a source emitting at period t of emission. Then in the meantime, the galaxy during emission is moving away. So the light must also, when it reaches us, it must also make up for the distance traveled by the galaxy during the time of emission, which is v times v of the galaxy times time of emission. So this is the distance that light must make up. So the observed period of emission will be, the observed period will be the period of emission plus the time that light takes to make up for this distance. So this distance, v times t of emission divided by the speed of light. And v will be positive if the galaxy is moving away, and it will be negative if the galaxy is approaching. So we can write this in terms of the wavelength, because the wavelength is c times the period, and so the period is lambda divided by c, and so we have lambda observed equals, since we are multiplying everything by c, equals lambda emitted plus the period of emission, which is lambda of emission divided by c. So we can write v in terms of the Doppler shift. V divided by c is lambda observed minus lambda emitted divided by lambda emitted. This is the Doppler shift, and it is called Z. So we have that v equals c times the Doppler shift. So if the galaxy is moving away, v is positive, so the observed wavelength will be larger, will be longer. So light will have red shifted. If v is negative, so the galaxy is approaching us, then the observed wavelength will be shorter than the emitted wavelength, and so the observed light will have blue shifted. In 1929, Hubble discovered a relationship between the Doppler shift of a distant object in the sky and its distance measured by luminosity. So there is a proportionality between the red shift, between the Doppler shift and the luminosity distance. This means that there is a proportionality between the velocity and the distance, because we have seen here that the Doppler shift is proportional to the velocity. This Hubble's law is written as v equals h0, the Hubble constant, times the luminosity distance, dl. So this means that the further away a galaxy is, the faster is its speed. So the more red shifted its light will appear. So this observation that faraway objects in the sky, faraway galaxies, are more redshifted, so have a high velocity, or they are moving away at a very high velocity, and this velocity is proportional with the distance, can be interpreted as the space being expanding in every point, so that further away objects they appear to be moving away more because there is more points of space expanding in a linear relationship, and this has consequences on the light that we observe. And so, for instance, if you take the microwave background radiation, that is cosmic radiation, which comes from when the universe had 300,000 years. So it has traveled almost the entire universe time, and that light, that radiation, has redshifted a lot in the meantime. So when we observe this radiation coming from the very early universe, although it was emitted in the infrared, we now see it redshifted in the microwave spectrum, and we must take this into consideration um, when we study the propagation of cosmic rays in space. And we must take into consideration that space is permeated by this microwave radiation. Now let's talk about magnetic fields. Extragalactic magnetic fields are much weaker than galactic fields, but acceleration regions in extragalactic magnetic fields are much larger, and so they can keep particles confined for longer. And in fact, we have seen with the maximum energy obtainable by a supernova that the maximum energy depended on the size of the supernova, and that the supernova could not accelerate at energies which correspond to a Lama radius larger than the supernova itself, because it would escape from the acceleration region than the particles. So we have in general the Helios criterion. The Helios criterion says that an acceleration region cannot accelerate particles to a Lama radius larger than the acceleration region. And so we had obtained this expression for the maximum energy obtainable by a supernova where L was the size of the supernova, the radius of the supernova in general. L is the size of the acceleration site, and usually Helios criterion is written not with eta but with beta, because eta was 4/3 u divided by c, which is about u divided by c equals eta. So Helios criterion is more often written like this. So we have that small acceleration region can accelerate particles to high energies if they have a large magnetic field. This is the case of neutron stars, for instance. And we have that regions with a weak magnetic field can accelerate particles to high energies if they are large. To visualize the size L and the magnetic field B needed to accelerate particles to a given energy, we can use a Helios plot. In a Helios plot, we have the magnetic field on the y-axis and the size of the region on the x-axis. So we isolate the magnetic field here, and we get E max divided by beta Z E C times 1 over P. 1 over L. And this plot is usually in a log-log graph. So we divide by b0, and we take the logarithm. B0 can be any unit of magnetic field, Emax by beta that is C, we're taking the logarithm with 0 times 1 over L. We want also the to separate the logarithm for L, so we divide L by L0, so we get an L0 here, which we can put here. No, sorry, we get an L0 on the denominator here. So this is equal to the logarithm of all this minus the logarithm of L divided by L0. So this is the y-axis, this is the x-axis, so we get y equals logarithm of Emax divided by beta that E C at 0 b0 minus x. So in a Hillas plot, the slope is -1, and where we begin here in the y-axis depends on the energy Emax. The higher the energy, the higher on the y-axis. So these are Hillas plots for different energies, and it also depends on the charge, because cosmic rays with a larger charge will have a lower y. Here is an example of Hillas plot. We have fixed the energy to 10 to the 20 electron volts, so this is a very high energetic nucleus, and we have the red line for Z equals 1, and the blue line for Z equals 26. So the red line represents a proton at 10 to the 20 electron volts, and the blue line an ion nucleus at 10 to the 20 electron volts. So the black spots are the position of the acceleration regions in the Hillas plot. And we can see if they are able to accelerate these nuclei. If they are above the line, they are able to accelerate them. If they are below the line, they are not able to accelerate them. So let's see, for instance, here we have neutron stars, this vertical line, because it has a variable magnetic field. So neutron stars are a very high magnetic fields, but they are very small, and so they are in this region of the graph, and according to this plot they're able to accelerate both the proton and the ion nuclei at this energy. And here we have gamma ray bursts. Gamma ray bursts are above both lines, so they are able to accelerate both of them. Then here we have white dwarfs. White dwarfs are an electronic version of neutron stars. They are a less extreme object than neutron stars, and they are much larger, but they have weaker magnetic field. And white dwarfs, according to this plot, are able to accelerate the ion nucleus to this energy, but not able to accelerate protons to this energy. And then we have here the active galactic the core of an active galactic nucleus, which are able to accelerate both of them. And then we have here the jet of an active galactic nucleus, which is like the expansion, the shock wave from an active galactic nucleus, which is a much larger area around the core, but it has an overall weaker field. But both of them are able to accelerate to this energy, cosmic rays to this energy, the core, because it has a high magnetic field, and the jet, because even if it has less magnetic field, it is larger. And then here we have radio galactic lobes, which can accelerate both of them. And let's see here we have the supernova remnants. We see that the supernova remnants are below both lines, and so they are not able to accelerate neither the proton or the ion nucleus. And then here we have the galactic disk, which is not able to accelerate cosmic rays of such energies, while instead the galactic halo, the magnetic field around the galactic disk, it is able to accelerate the ion nucleus to this energy, but not the proton. When cosmic rays travel in intergalactic space, they suffer energy losses. The most important of them leading to the Greisen-Zatsepin-Kuzmin cutoff, and this cutoff is due to cosmic rays losing energies due to interaction with the microwave, with the cosmic microwave background. So photons in the microwave, for high energy cosmic rays, because of relativity, it looks to them like a high energetic gamma ray, and so a very energetic collision happens, and the process is this: the proton cosmic ray collides with a photon of the cosmic microwave background and produces a resonance delta plus, which quickly decays either into a proton and a pion pi 0, or into a neutron and a pion pi plus. So the proton is, as far as we know, which is stable. The pion, the neutral pion, instead decays into two gamma rays. The positive pion decays into a positive muon and a muonic neutrino, while the neutron decays into an electron, a proton, and an electronic antineutrino. So we have two possibilities. One is that in the end we have gamma gamma and proton, and one is that we have mu plus, ionic neutrino, E minus, antielectronic neutrino, and proton. So in either case, we have the proton in the end, but it will have the energy will be shared between the other particles, and so it will have lost energy. Now we want to find the energy threshold for this process. So we have to consider the full momentum of these quantities. So E proton divided by C, and we must sum them. So we have E proton plus E gamma ray divided by C, and P proton plus P gamma ray. Now we take the modulus square of this full vector. We have EP plus E gamma squared minus PP minus P gamma squared divided by C squared. So we have taken the modulus squared and multiplied it by C squared, and we have this relation that this must be at least the mass of the resonance, and so the energy threshold is for this equal to mass of the resonance squared times C to the 4. So we have EP squared plus E gamma squared plus 2 EP gamma minus the modulus of P squared minus the modulus of P gamma squared minus 2 times PP times P gamma times the cosine of theta, when theta is the angle between the photon and the proton trajectories, and multiplied by C squared. Although this multiplied by C squared, let me rewrite better. C squared minus P gamma squared C squared minus 2 pp gamma cosine of theta c squared. And this must be equal to this. And so we have this minus this is the mass of the proton squared times c to the 4. Then we have this minus this is 0 because for the photon we have that momentum is E divided by c, the modulus of the momentum. Then we have plus 2 EP E gamma, and then we have minus 2. Now we can write P gamma as E gamma divided by C, but we can do also this approximative for the proton because it is a relativistic proton. So EP divided by C and E gamma divided by C times the cosine of theta times C squared, so we cancel C out. This equals to m delta squared C to the 4. So we can now isolate EP, and we get EP times, let's write directly, EP equals m delta squared minus mp squared times C to the 4 divided by 2 E gamma times 1 minus cosine of theta. Oh, and I had written a minus here instead of a plus sign, but I did the calculation correctly anyway. The minimum energy threshold is when the denominator is larger. So when cosine of theta is smaller, so when it is equal to minus 1. So the so cosine of theta equals to minus 1 means head-on collisions, and in which case EP minimum is equal to m delta squared minus mp squared times c to the 4 divided by 4 E gamma. And we can calculate this. This is about 10 to the 20 electron volts. So the region of the cutoff is, as we had anticipated in the first video, 10 to the 20 electron volts. But since the microwave region spans a certain range of energy, there are higher energy photons, so this would be for by plugging in an average energy for the microwaves, but the higher energy photons will interact, will have a short energy threshold and start to interact with the protons of less energy than this, and it is considered to the cutoff is considered to begin already at 5 times 10 to the 19 electron volts. So this is for protons. For higher nuclei, we have that instead of a proton, we have a higher nucleus, but the process happens for one proton. So the threshold remains the one for the proton, which means that the higher nucleus we have A times this energy. So the energy threshold, where A is the mass number, the energy threshold for a nucleus is A times the energy threshold of a proton. So there is a proportionality with the mass number of the cutoff region, which if you compare with the knee region and the ankle region, which had a magnetic nature, they depended on the charge, so the proportionality was with Z, the atomic number. Here instead the proportionality depends on the energy, so on the overall distribution of energy in the nucleons, and so here the proportionality of the cutoff is with A. So we have that cosmic rays with energies higher than this cannot travel very far, and so all those which we observe at this energy must be from of nearby origin. And so we have that. We have seen the structure of the knee, which is the inability of supernova remnants to accelerate cosmic rays, and then we have seen the structure of the ankle, which is the inability of the galactic field to contain the cosmic rays, and then we have seen now the cutoff, which is the cosmic rays losing energies when traveling in intergalactic space. And with this third video, we end our discussion about cosmic rays. See you next time.